Hello, everybody, and welcome to episode 12 of our video series in which we program an entire video game from scratch, from beginning to end. First thing I want to do is talk about a couple of viewer comments that I received last time. All right, one viewer says, okay, this viewer says, I'm not familiar with Windows Mutex, only with Linux Mutex, but shouldn't you destroy the game Mutex before exiting the application? Or Windows handles that for you? Let me open up the game. Short answer is yes, Windows handles that for you. For the exact same reason. Oh, and by the way, he's talking about this Mutex right here. If you don't recall, Visual Studio Update. We'll do that some other time. If you don't recall, what he's talking about is here in this little function that we wrote towards the very beginning that determines whether another instance of this game is already running or not, and the intent is to try to only allow one instance of the game to be running at a time. And then so when you create it, there is also like a I guess I better just look up the function. There is a way to destroy a mutex. I don't remember if it's just close handle or if there's a special destroy mutex function. Let's look it up. There it is. No way. That's not it. Release mutex is not what we want. There we go. Use the close handle function to close the handle. The system closes the handle automatically when the process terminates. So that's the answer. Is the reason why I don't specifically close this mutex is because Windows automatically does it for you in a user mode process. That's an important distinction. Is that when you are writing a user mode process in Windows, Windows will automatically clean up all the resources that you have used as soon as your program or application exits. So it's the same reason why, it's the exact same reason why when I go down here and I allocated this memory, I don't have to worry about freeing that memory when my game exits, because when my game exits, Windows will automatically clean up all the resources that I have allocated throughout the life of this entire program. In fact, you actually shouldn't make any special effort to free any resources specifically on your way out. When your process is exiting, you should trust and rely on Windows to clean up any resources that your program was using as it exits. If you try to free everything yourself, it's just gonna make it take longer to exit the application. It's just gonna make it take longer to for the game to quit. I don't if you've ever been playing a video game and it's a big AAA title. It's got fancy graphics and everything, and you go to exit the desktop and it takes like 10 seconds from the time you hit the quit to desktop button to the time that the game actually stops running. All of that deinitialization stuff, depending on what it is, probably doesn't need to happen, and you're just kind of just wasting time. You should just let Windows clean it all up for you. All right, so I've said that enough. Let's move on. Okay, another viewer says, is there a way to query to get what CPU instruction extensions that the program is currently running on? Is there a way to query to get what CPU instruction extensions that the program is currently running on? Also, do AMD processors have SSE2 instructions, for instance? Okay, so what this person is talking about is the really awesome stuff that we did in the last episode where for a second there, we just like lost it and it went back to the old uh, mem set, and I was like, oh no, what happened? But no, we moved it to this clear screen function, and we changed one line of code, and turned our mem copy or mem set uh, into an SSE or SIMD intrinsic, and that allows us to basically write 128 bits at a time instead of 32 bits at a time, thereby practically quadrupling our performance. If you remember, our raw frames per second went from something like 450 FPS to something like 2500 FPS, just with one line change. And before I forget, I should also mention that I went ahead and included the emm intrend.h header file. I changed this data type to a 128-bit data type. I went ahead and made this loop increase by 4 pixels at a time instead of by 1 pixel at a time. And then I'm slapping down 4 entire pixels at a time instead of just 1 pixel at a time using SIMD nomenclature or function names, data type names. But what's important to note is that I may have actually, and I don't know this for a fact because I haven't looked at the disassembly when I try, but it's important to note, and we may experiment with this later, I may have actually been able to achieve the exact same results if I had just increased this loop count to 4, and if I had just changed my data from from a pixel, which is 32 bits, into an array of pixels, which is 4 32-bit pixels, so it's 128 bits. If I had done that, I may have, quote unquote, magically achieved the same results because the compiler optimizer might have seen that what I was doing, and the compiler, would have caught on to it, and he would have said, "Oh, he is writing these 128 bits at a time. This is a perfect job to jam this data into those XMM registers instead of using the conventional standard purpose registers." And the compiler might have automatically optimized this for us. But I didn't know if the compiler was going to optimize it for us or not, so I went ahead and showed you all the SIMD stuff because you needed to be introduced to it anyway. But back to the viewer's question. He wants to know how can you tell if the CPU that you're running on is able to support any of this stuff in the first place? And the short answer is with the CPU ID instruction. It is right over here. Let's see, CPU ID. And there's also an application called CPU ID, which is not to be confused with the CPU ID instruction, the intrinsic. This generates the CPU ID instruction on x86 and x84, x64. This instruction queries the processor for information about supported features and the CPU type. And I think there's probably some example. There is. All right, so if you issue this CPU ID instruction, it will return to you all kinds of bits from which you can extract exactly what features the CPU supports. AVX2, MMX, all this kind of stuff. All this kind of stuff. You can tell exactly what the CPU supports and what it doesn't. Now, am I going to do this? I mean, you could potentially run a test or a function like this at the beginning of your program and get whether the CPU you're on supports SSC instructions before you use them, and then just have an if statement in your rendering code that says, if SSC is supported, then do this, else do it the old-fashioned way. That would be okay. But am I really going to do this? I don't think so. I think what I'm probably going to do instead is I'm probably just going to define a switch called SIMD, and I don't know if I want it to have an underscore. I'll just have it like that. Alright, so I have pound defined SIMD, and then if I go down here, I'm going to do if defined SIMD, then do that stuff. And these, if you are not familiar, these are pre-compiler directives that I'm putting in here. So when I compile this code, it's not actually going to be part of the logic that the CPU executes. The compiler is going to make the decision on what code to compile at compile time. So it's going to result in two different executables, whether I have defined SIMD or not. So at the end of the day, I would end up distributing two different copies of this executable. One which supports SIMD instructions and one which does not. So, and remember, instead of, when we're not using SIMD, we just go up by 1 pixel at a time instead of 4 pixels at a time. And instead of doing that, we do memcopy pixel 32. This is a pointer to a pixel. And, well, shot myself in the foot here. This isn't going to work because we only supply 128-bit data type. So, what I think I'm going to have to do is this. I'm going to have to write an entirely new function. And it takes in a pixel 32 pointer. A pointer to a pixel, and we're just going to call it pixel. Now, I want to move my if statement around a bit. Or maybe just pixel. Okay. So there's still more that we have to do, but notice how it's this. This is grayed out right now, and this is not, because right now we have SIMD defined, so it's telling us that right now we're going to run this version of the code. But if I go back here and I don't have SIMD defined, then it switches the other way around. So memcopy then I have to go back up here to render frame graphics, and I have to do the same thing. If SIMD, then do that, else, you know, do something with then we have to do the same thing over here. Making a new function declaration. Pointer to a pixel. Alright, move over here. Pixel. Let's make this. Send it the address of the pixel. Now, does it build? Yes, it does. Does it run? Yes, it does. $1600 FPS. Isn't that odd? Isn't that odd? The other day when we had this logic in here, clear screen pixel, we were getting something like 450 FPS last time, remember? What are we doing differently? Let's go to the, let's run to cursor here. It doesn't look, I mean, it doesn't, it's not, looks pretty conventional to me. So let me stop. Let me turn SIMD back on. And now let me run it again and see what happens. Yeah, see on this version of the function, you can clearly see that I'm using the XMM registers and I'm using SIMD instructions. So let's see what my frame rate actually is. So yeah, I'm getting over, I mean, like a 2500 FPS frame rate. I don't know why that's flickering. Also, I noticed my FPS seems to go down as soon as I turn the debug text on. Notice that my average goes way down, like 1000 FPS, as soon as I turn the debug text on. When I turn it off, I can't tell what my FPS is, but when I turn it on, it's like it's like 3500 or 4000. And then with the debug text on, it drags it back down to 2500. So that sucks a lot too, and we're definitely going to have to figure that out. In addition to why it's flickering. But anyway, so the other part of the viewer's original question was over here on my other screen. Yeah, basically he just asks um, if we can assume that SSE2 will be present on AMD processors. And the answer is yes. SSE2 specifically is very old by now. It's like 20 years old. So it's safe to assume that you will find SSE2 supported on any x86 or x64 processor that was manufactured in the last 20 years. Um, Pretty safe to assume that. The only time that you can't assume the presence of SSE2 is if you are working with either a very, very, very old vintage processor from like 1990, or if you're working on a completely different platform like ARM or PowerPC or something like this. Those processors have their own different versions of SIMD, and I'm not sure that they support all the same instructions. So you might have to go do your own research if you're using those kinds of processors. Um, Similarly, like AVX, where did I see it? AVX512, for example, is an example of a very new SIMD version, and not all processors have that. So even if your processor was made in 2020, there's no guarantee that it's going to support AVX512. So you definitely can't assume the presence of that. Okay, so here that does it for the viewer questions, but this gives me what we just did gives me something else that I should probably work on. um, I want to figure out why our FPS is so much higher now. Oh, one other thing, totally spaced out on this. uh, Back on the which features are supported on which CPU, uh, takes us back to sysinternals. There's another sysinternals tool called CoreInfo, and it will give you all the same stuff. It runs CPU ID on your processor, and it tells you everything you want to know about your processor in terms of what it supports and what it does not. So you can see, I've got SSE, SSE2, and my Intel processor. It actually says it does not support 3D Now or 3D Now extension instructions. I guess SSE1, the SIMD wars. I don't know, but yeah, it looks like I support all the way up to 4.2, and I don't think Core Info has been updated to even show whether my processor supports AVX512 or not. I assume that it does not because AVX512 is really new. But anyway, so that's core info from sysinternals.com. Okay, so back to this. It's funny because I was just talking about how the compiler might have been optimizing this even without explicitly using SIMD. Um, but then today we're getting vastly different FPS than we were the last time. So what's up with that? All right, so the first time, let's make this consistent. I want to pass pointers to both of these functions. That's fine. See if it runs. Runs perfectly fine. Good FPS. Let's run the regular version again. Interesting. It's even a bit faster in release mode. About 3000 FPS. The question is though, why is my debug text flickering today when it wasn't flickering last time? I'm really bummed out about that. There's something else that I need to fix too. Our arithmetic is wrong right in here. And I say that because if you recall, our intent here, this is our main game loop in our WinMain function. And my intent right here was to say sleep for the smallest period possible unless the sleep would put us beyond our 60 FPS or 16,667 microsecond target. And the reason this is wrong is because we're not comparing apples to apples here. This is in 100 nanosecond units. This current timer resolution value is in 100 nanosecond units, and then target microseconds per frame obviously is in microseconds, 16,667. So this is incorrect. Let me run to cursor here. And let me just look and see what current timer resolution is. So if you look at the minimum timer resolution, which is 15.625 milliseconds, this has a value of 156,250. So let's see, 156,250. If we divided that by 100, 1,000, 10,000, we get milliseconds. What do we have to divide it by? Oops. Yeah, 15,625. So if we divide that number by 10, we get microseconds. So current timer resolution is 9,973. 9,973 divided by 10 is 997.3 but that's milliseconds, right? I think I would like to take this opportunity, though, to go ahead and clean up this name. I don't think there's any reason to have per frame on there. Per frame. Per frame. Per frame. Yeah. So our problem right now is we're not sleeping at all, which is why our CPU usage is so high. Okay, so current timer resolution is 9973, and if I multiply that by 0.1, then I get 997. Which is microseconds, right? All right, 997 microseconds is about 1 millisecond. So, okay. Now let's see what we look like. So our cooked FPS is back down to around 57, but our CPU usage has also gone back down to almost nothing. So I think I would rather have 57 FPS than 100% CPU. So I guess we're just going to have to live with that for now. Okay, second thing is on render frame graphics. remember that, okay, this part where I'm drawing the debug info, I think instead of actually trying to debug that and see why it was flickering, yeah, see it's flickering a little bit. I think instead of trying to figure that out, when we get to the point where I can draw my own text on the screen instead of using the Windows API, then I will replace all of this anyway at that time, so I'm not going to worry about it for now. This is just temporary, all of this stuff. So let's move on and do something totally different now. This little code section right here, this is where we drew that little square, and I think I want that little square to become our player. And the first thing that needs to happen is let's make a player, let's make a data structure to represent our player. And we're going to call it type def struct player. Okay, so this is going to be a pretty large data structure that's going to have a lot of things in it. But the first thing we'll have in it is going to be a world position X and a world position Y. He's also going to have things like name, for example. He's probably also going to end up having things like you know, HP and strength and you know, what else? MP for magic points, maybe something along that, something along those lines. But this will get us started. All we really care about right now is just the X and Y coordinates, because we're going to use that. We are going to use that. G. Oh well, can't do that yet. Let's go back up top and make a player. And then somewhere before our game starts running, I will probably need to initialize our player. I'll probably make some function called, you know, initialize player or something, but for now let's just do dot world position X equals 25 and gplayer dot world position Y equals 25. Okay, now we go back down here. gplayer dot world position X, gplayer dot world position Y. Everything's fine. Okay, now let's go to our process input function and let's start accepting movement keys. Int 16. We'll say left key is down equals get async key state vk left. Int 16 right key is down equals get async ek right. Now, what if I wanted to say, like, you could also move, instead of moving with just the arrow keys, what if I also wanted to move with the WSAD keys instead? Or what if I also wanted to tack on input from another type of controller, like a gamepad? So we could also just do a bitwise OR here and say that our right key is considered to be down if either of these things are true, or if either of these things are not null. VKW. Oh, let's see. I gotta look at my virtual key codes. Virtual key codes. W is 57. I suppose I could do this, couldn't I? It translates to an integer, which is 87. No. Oh, it said hex. Yeah, hex 57. That's 87, isn't it? So, yeah, I think that's fine. Oh, except it's not fine. I want it to do left instead of right. And this would be D. Okay. And remember, for each key that we want to get the state of, we also need to make a static counterpart for was it down. Left key was down. Left key is down. Okay, and then finally, the last thing we need to do is record the state of each key as we leave the function. Left key was down equals left key is down, and right key was down equals right key is down. Was. Okay. Now, what is the deal here with the typos? Right key was down. Right key was down is was. Okay. Now we're going to do if left key was down and not, sorry, I messed this up. We want to do if left key is down, but it wasn't down the last frame, then we're going to do G player dot world position X -1. If right key is down and not right key was down, then we're going to do G player dot world position X +1. Alright, let's see what happens. So now you can see I can move my thing to the left and right. Got that wrong. I don't know why I thought left was W. It's obviously S. S and W, A, S, D. A. A is left. You know, I've only been gaming for 35 years. You would think that this wouldn't come so hard to me. A is left and D is right. Let's try that again. Okay, so now I can move my character back and forth, left and right, by using the keyboard, which is pretty cool. The downside is that it's set to where I can't hold the key down, though, and that's obviously no good. Nobody likes that type of movement for an RPG, so this is going to be interesting, though, because if I take this part away, if I take this part away and this part away, it's gonna work, but now I'm moving at 60 FPS basically, or 57, moving at 57 pixels per second basically, which that looks okay. This might be a bit fast, so we're gonna have to artificially slow it down, I think, but for right now it's fine. So there's another thing I want to point out is watch what happens when you get off the edge of the screen is you wrap around to the right side of the screen. And if you recall from when we are drawing our pixels, remember that our back buffer is drawn from, or basically the memory addresses that comprise our back buffer start at the bottom left hand corner of the screen and then draw from the left over and basically fill from left to right, bottom to top, all the way up until you get to the top right hand corner of the screen, at which point you've reached the end of your memory address space. So what I'm trying to say here is when you wrap around, you are actually going to be moving up 1 pixel. So I could keep moving from left to right like this, and every time my character wraps around the screen, he's actually shifting up 1 pixel. And once I finally get to the top right hand corner of the screen, if I move off the top right hand corner of the screen, the game will completely crash, because remember, you cannot draw anything past the end of this memory buffer. So we're definitely going to have to account for that. But let's go ahead and finish this up here. So int 16 up key is down equals async key state vk up, or get async key state w, right? Int 16 down key is down equals get async key state vk down, or get async key state s, no, WSAD. Yeah. Int 16 right up key was down, static int down key was down, if down key is down, then gplayer.world pose y +1, because remember our X and Y origin is the top left hand corner of the screen right now. We may change that later if it becomes confusing. I don't know. Key is down. This is G player dot world pose Y -1. Do up key was down equals up key is down, and okay, let's see what it looks like now. There we go. We have full two-dimensional freedom of movement. As I said before, I'm going to avoid touching the edges of the screen, especially the top and bottom edges of the screen, because, like I said, once you start trying to draw anything that is not within your address range of memory addresses for your back buffer, the entire game will crash. So don't even try it. In fact, I guess I'll go ahead and show you. I'm going to intentionally crash the screen now, or crash the game now, by trying to leave the screen. Boom. Instantly, we crashed. So I'm going to go ahead and stop. And I'm going to put some, let's see, I'll go ahead and put a guard in against that. If G player dot world pose Y is less than game res height minus well, we know that our player's height is 16 pixels, so just put it like that for now. No, put it in the wrong place. Not left key is down. Down key is down. If my Y position is less than that, then move it down. Let's see what happens now. See if I can still crash the game. No, perfect. Works perfectly. Now I can slide along the bottom of the screen without crashing. And if you look closely, you'll notice that once I moved off the side of the screen and wrapped around, that I also moved up 1 pixel at the same time. Now I've moved up 2 pixels. So we'll have to deal with that. I can just do the same thing for the right and the left so that you can't move past the right hand side of the screen. Let's go ahead and finish this out. Let's see, up key, if the world position is less than, let's say if the world position is, if my Y coordinate is greater than 16. I think that should do it. Oh, no, that doesn't do it. There we go. So now I cannot move past the top and bottom of the screen. Let's do the same for the left and right. If my player.worldPoseX is greater than 0, Then go ahead and move me left. And over here, if my X position is less than my game resolution width minus 16, then go ahead and move me to the right. Let's see what it looks like now. Okay, I cannot move past the left-hand side of the screen. I cannot move past the top. See if the bottom works. Of course it does. Yep, everything works perfectly. And I no longer have to worry about crashing because I moved off the edge of the screen. So yeah, from here you can do all sorts of cool things, like if you're holding down another button, it makes your guy run even faster than he's running now, for example. You can do all sorts of cool stuff from here. So we did get something accomplished today, which is nice. Okay, so what are we going to do next time? We might get into sound next time. I'll go ahead and in the meantime try to debug some of these issues, like why my FPS was 450 the other day and now it's above 1,000 even when I don't use SIMD, because I genuinely don't understand that, and I would really like to understand that. And then of course I will work on this a little bit. You're probably getting tired with this microseconds per frame stuff, and I am too. I would like to get it perfect so that we can stop playing with it. Yeah, so next time we might get into some audio. It's getting about that time. Oh, well, actually, before we do audio, we should probably do bitmaps. Yeah, bitmaps would make more sense to start with next time. So things like loading images from files and then pasting those onto the screen, because obviously we don't want to draw everything programmatically. We want to be able to just to load bitmaps off of the file system. So that sounds like a good next step. Anyway, so I think that brings us to the end of episode 12, and as always, thank you for watching. If you have any comments, just leave your comments on the video, and I will address them in an upcoming episode. And please like and subscribe and all that good stuff. Until then, stay safe out there. See you next time. Bye.